Hello everyone, my name is Ida Salim and today I'll be discussing significant figures, how to add and subtract, multiply and divide, taking logs, combined operations, and also scientific notation. Before I go into significant figures, I'd like to talk about scientific notation, how to convert from the number to the scientific notation, and vice versa. So to begin with, the first example I'd like to talk about is 1,000. How do I rewrite this in scientific notation? Well, that's basically going to be 1 times 10 to the third power. And how do I know it's to the third power? That's because you know that there's a decimal point always at the end of the number to the right of it. You're going to move the decimal place as many times you need till you get between a number that you can't continue further. So we moved it 3 times, 1, 2, 3 times to the left, so that's why it's to the positive third power. Okay, so if I had an example that is a little different, for example, 0.001. If I want to rewrite that, I have to bring this decimal point 1, 2, 3. So then my answer would be 1 times 10 to the negative third power. Do you guys see the difference? The first example, you had the decimal point to the right of it, right here. And the second example, you had the decimal point towards the left. So now the rule is going to be, if you are going from a number to scientific notation, you're going to basically figure out this. If you're moving to the left, your exponent, it's going to be 10 raised to a positive number. If you're moving to the right, it's going to be 10 raised to the negative number. Again, if I, like this example, the first example, I move to the left, so it's 10 raised to the positive 3. The second example, I move to the right, so it's 10 raised to the negative 3. Let's do another example so you see it better. If I had 650,000, and I want to rewrite it in scientific notation, I know that there's a decimal point here, so I'm moving to the left. 1, 2, 3, 4, 5, and I stop here because that's the most I can go, and I get an answer of 6.5 times 10 to the 5th power. It's positive because I moved left. Let's do another example. 0.00004306. Move the decimal place to the right. 1, 2, 3, 4, 5. So I get an answer of 4.306 times 10 to the negative 5. And it's negative because I moved to the right. Now, if I was going vice versa, or the opposite way, where I'm going from the scientific notation to the number, it's a little different. So, for example, if you had a number like 1.034 times 10 to the 6th power, that's basically telling me that I'm moving the decimal place 6 times to the right. So basically it's going to be 1, 2, 3, 4, 5, 6. So I get an answer of 1034. And because there's no numbers here, I'm going to replace them with zeros. 1, 2, 3. And the answer is that. If I have another example, like 5.07 times 10 to the negative 5, what's that telling me is that I'm moving the decimal place to the left 5 times. 1, 2, 3, 4, 5. So then my answer is going to be 0.00000507. Basically, what I did was I replaced everything with zeros. Let's do another example where you have 2.204 times 10 to the fourth. You end up getting, you're moving it 4 times to the right. So you're getting 1, 2, 3, and 4. Fill this in with a 0. You get an answer of 22040. And the last one I want to do is 4 times 10 to the negative 2 power. So you're moving to the left 2 times. So you have 1, 2. And I'm going to fill this in with a 0. And then I get an answer of 0.04. Okay, so the rule is going to be, if you are going from the scientific notation to the number, you're going to have, if you have something raised to the positive power, you're moving to the right. If you have 10 raised to the negative power, you're moving to the left. Make sure you practice this because it's very important. Accuracy versus precision. Accuracy is how closely a measured value agrees with the correct value. Precision is how closely individual measurements agree with each other. So, what does this exactly mean? I'm going to explain using these bullseye graphs or pictures. And we're going to determine how accurate and how precise each picture is. So if you look at the first one towards the left, you have all 3 darts that are not in the red bullseye area, so that makes it very low in accuracy. And precision, well, all the darts are not closely together, so they're very far apart. This is far apart from this, and that's far apart from that. So the precision is also very low. Now if we look at the second diagram, you notice nothing is in the red area. So again, it makes it very low in accuracy. But because all 3 darts are jumbled up in the same area, it makes it very precise. So high in accuracy. The third diagram basically has all 3 darts in the red bullseye area, so obviously it makes it very accurate. And if you look at the 3 darts, they're not so together. This one's not so close to all 3 compared to the second diagram. So that's why the precision is low. And the last diagram, it's very clear to see that it's very accurate because everything is in the red area. And because all 3 darts are all together, jumbled up together, it makes it very precise. So now let's get into significant figures and its rules. So the first rule is saying digits 1 through 9 are significant. So for example, if you had something like 129, well, that means you have 3 sig figs. Why? Because 1, 2, and 9 are significant. The next one says all zeros between significant digits are significant. So for example, if you had 5007, you're going to have 4 significant figures. And why is that? That's because these 2 zeros are in between a digit 5 and a digit 7, so it totals to 4 significant figures. All zeros which are to the right of the decimal point. For example, if you had something like 105.0, well, this 0 is to the right of the decimal point, so you will end up getting a total of 4 significant figures. All zeros that are trailing after a digit 1 through 9 is not significant. For example, if you had this number, this means that you have this 0 that is trailing right after a digit that's 1 through 9. So you have a total of 5 significant figures. Now this is where it gets a little tricky because this could have 5, but this number can also have 6 if you write it in scientific notation. So if I wrote this number in scientific notation, you'll end up getting 1, 2, 3, 4, 5. You'll get 3.1658 times 10 to the 5th. If you write it in scientific notation, you end up getting a total of 6 significant figures. And that's because this time this 0 counts. Okay? This 0 counts because it's following this rule. All zeros which are to the right of the decimal point. Yes, this 0 is to the right of this decimal point, so that's why it counts, totaling 6 significant figures. The last example I'd like to do is 0.0076. So these zeros do not count, so you only have a total of 2 significant figures. So real quick, let's do some more practice with our sig fig rules. Find an example of pi 3.14159. You have a total of 6 significant figures. If I had 1,000, this would be 1 sig fig. But if I changed 1,000 into scientific notation, like this time I'll get a total of 4 significant figures. If I have another number like this would be 2 sig figs. If I had this would also be 2 sig figs. 560 would be 2 sig figs. But if I change 560 into scientific, that would be this time 3 sig figs. If I had a 10320, this would be 4 sig figs. But if I had 1.0320 times 10 to the 4th, which is the same number but in scientific notation, this time you have a total of 5 significant figures. And if I wrote the number as 10320.0, you'll have a total of 6 significant figures. So here, all of these are significant. Over here, all of these are significant. And over here, all of these are significant. Okay? And my last example is 5.230. You get a total of 4 significant figures because every single one counts. I'll also be talking about rounding because it becomes very important when we're computing different types of problems. I'd like to teach this using just examples. So my first example is 52.39. We want to round this to the nearest ones place, which is our 2 here. If I want to round that, I have to look at my right side, and I know that 3 is less than 5. So if it's less than 5, we're going to have to drop everything and just write with what we have left over, and it rounds to 52. The next example is 68.589. This time I want to round to the nearest tenths place, which is the 5 here. We look at the next door number to the right. We realize that 8 is more than 5. So we have to increase this number by 1. So if we increase that number by 1, you end up getting 68.6. The next number is 162.582, and I want to round to the nearest 100, which is right here. I look to the right of it. I realize that it's more than 5, so I basically increase this number by 1, and I end up getting 200. And my last example is 5.5062, and I want to round this to the nearest thousandth place, which is our 6. We look to the right of it. We realize it's less than 5, so we drop this, and we end up getting 5.506. When taking log of a number x, the number of significant figures in the number x is equal to the sig fig numbers in the mantissa of the answer. So what does that mean? So let's start off with an example of log of 265. If I put this in the calculator, I get an answer of 2.423245874. And I want to report this the appropriate number of sig figs. So the number 2 here to the left of our decimal point is our characteristic. And everything over here is our mantissa. So what I have to first do is understand how much sig figs I'm dealing with in my original number x, which is this. So here I have 3 significant figures. So my answer's mantissa should also have 3 significant figures. So the mantissa's here, and I need to stop at 3 sig figs. 1, 2, 3. So this is what I'm going to report right here. And if you round appropriately, you get an answer of 2.423. So let's look at another example. If I had log of 3852. If I put this in the calculator, I get 3.585668278. And let's talk about first how many sig figs we have in our original number x. This is 4 significant figures. So my answer's mantissa, which is here, should also have 4 sig figs. 1, 2, 3, 4. This rounded appropriately will give you an answer of 3.5857 as your answer. So your sig figs of your original number should equal to the significant figures of your mantissa. Adding and subtracting is basically dependent on this rule. The answer is significant to the least amount of decimal places. So to begin with, we can add 2.457 with 2.5. We add these together, we get 4.957. So we have to be mindful of how many decimal places we're dealing with. So the top number we have 3 decimal places, and the bottom number we have 1 decimal place. So it's saying it's going to reflect the least amount of decimal places. So it's going to be 1. Our answer is going to hold only 1 decimal place. So we're going to look at the first decimal place and round. See how much rounding is important? Because that's 5 and up, this number bumps up to 5.0. And it's to the 1 decimal place, right? Let's do another example. We can do 25.6 minus 20. You end up getting an answer of 5.6. Let's be mindful of our decimal places. We have a total of 1 decimal place here and 0 decimal places here. So we need 0 decimal places in our answer. And we notice that's where we're going to stop. So we want this to be 0. So we look at this number 5. We look here and we round. Okay, well that's 5 and up. So this number has to be bumped up to 6. And that would be your answer. Multiplying and dividing, it says the answer is significant to the least amount of significant figures. So what does that mean? Let's look at an example. We have 8.56 times 10 to the negative 4. And we're going to multiply this by 1.2223 times 10 to the negative 5. We get an answer of 1.046288 times 10 to the negative 8. That's what the calculator told me. Now, in terms of significant figures, we want the least amount of sig figs, so we're going to figure that out. Here, we have a total of 3 significant figures, and here we have a total of 5 significant figures. Let's make it neater. Let's say 5. So what's the least amount of sig figs? It's going to be 3. So 3 would be 1, 2, 3. So we're going to stop at the 4 and then we're going to round. So that would be 1.05. If we look at another example, we'll do division. We could do 4.12 divided by 7.882. When I did this in a calculator, it gave me an answer of 0.52270999721. Now we need to determine the appropriate amount of sig figs. So here we have 3, and here we have 4. So we want the least amount of sig figs, which is 3. So we're going to do 1, 2, 3, and round. So if you round correctly, it would be 0.523. And that's all it is. Combined operations, this is when you're adding and dividing at the same time, or you're subtracting and you're multiplying at the same time. So you have to keep track of significant figures and your PEMDAS rules. Remember, PEMDAS means P for parentheses, E for exponents, M for multiplying, D for division, A for addition, S for subtraction. That's from what you learned in algebra. Then you're going to use the appropriate amount of sig fig rules. So you're going to ask yourself, what is the next operation I'll perform on the number that I just calculated? If the next operation is in the same group of operations that you just used, then do not round off yet. If the next operation is from the other group, meaning different group, then you must round off the number before moving on to the next operation. So let's take a look here at an example, because it may sound confusing at first. So if we had an example like 4.85 times 12.14 divided by 0.020. So what do I have to do? Do PEMDAS. I see multiplying first, so I'm going to multiply that out. So I end up getting 58.879 on the top. And then I ask myself, I'm going to go to the next operation, and if it's in the same group, we do not round off yet. So my next operation here, I'm dividing. Multiplying and dividing are in the same group of operations, so I am not going to round off just yet. So this is what my calculator read to me, 58.879. I'm going to go ahead and divide by 0.020, and then I'm going to figure out my sig figs. Multiplying and dividing, remember, is the least amount of sig figs. So over here we have a total of 5 sig figs, and over here we have a total of 2 sig figs. So my answer, when I divide these out, I end up getting 29.4, so 2943.95. So I want a total of 2 significant figures, so I'm going to go to this and I'm going to round. So that rounds to 2,900, and that would be your answer. So it just comes with practice, and again, you have to start from the basics. Know your sig fig rules. You want to know how to round, then you want to know how to do adding and subtracting, then multiplying and dividing, and then combining them all together. So everything is dependent upon each other. So that's what I have to talk about with sig figs. And I hope you learned, and it bettered you in your sig fig rules. So this is a try on your own slide, exactly what it means. Try to be independent. Use what you learned today to solve the problems and check the answers. I do want to point out that for number 2, the answer is 0.30 grams per liter. And remember that practice makes perfect.